Video 3 of Chapter 7, we're going to get into some actual calculating and interpreting of numbers finally in here. We're going to be focusing on less theoretical stuff and actually focusing on some actual stuff. Now, in video 3, we're going to be talking about looking at sampling distributions of sample proportions. Okay? And there's going to be some differences between sampling distribution of sample proportions and sampling distributions of sample means that we will talk about in videos 4 and 5 upcoming. Um, the main thing I want you to get right now in proportions and means is that they are both unbiased estimators that we talked about in video 2, and that's the main reason why we're going to focus our attention on sampling distributions, on sample proportions and sample means, is because they are unbiased estimators. So first, the shape of a sampling distribution of sample proportions. A sampling distribution for sample proportions will be approximately normal if this following condition is met. So the n is our sample size and the p is the population proportion. If we don't know what the population proportion is, we're going to have to use our sample proportion as a backup. But if we were to multiply the sample size with our proportion and our sample size times 1 minus the proportion, both of those values need to be greater than or equal to 10. And you might be wondering, what if one of those conditions isn't met? What's that really mean is true? Well, what that means is that our distributions are not approximately normal. It means that they are either skewed left or skewed right. And if it's less than, if n times p is less than 10, then we are dealing with a skewed right distribution. And if the n times 1 minus p condition is not met, then we are dealing with a skewed left distribution. And if we are dealing with skewed distributions, we're not going to be able to use an approximately normal distribution to calculate some probabilities. So it is very important that you check this condition. This will be something that I will check for, no pun intended. Number 2, the center. Since the sample proportion is an unbiased estimator, then the mean of all of the different sample proportions that we could theoretically take, which we aren't, would be equal to the true population proportion P. Okay, so the mean of all our sample proportions will be approximately our population proportion. And the spread, specifically the standard deviation. The standard deviation of all possible sample proportions, we're going to call this sigma sub p hat. Sigma sub p hat. The standard deviations, or the standard deviation of all of our sample proportions that we could gather from our sampling distribution that we're not, because we're only going to take one sample, but theoretically, it would follow this formula here, that sigma sub p hat would be equal to the square root of all of this loveliness. And once again, if we don't know what the true population proportion is, then we can replace p with p hat, the sample proportion. And why can we just replace p with p hat? Because p hat is an unbiased estimator of what the true population proportion p is. Now, this also has a condition tied with it. Is the population at least 10 times our sample size? Now, this is what's referred to as the independent condition, or you might see it in the book called the 10% condition. And the truth is, we can't sample too much of our population, because then we're going to start to know more and more and more about our population, and at that point, we don't really need statistics to help estimate what the true value of the population is. So our sample size times 10 needs to be smaller than the size of the population. And another truth here is, how big is the population in most instances? You're not going to know. So what we're going to do in these situations is we will just say the population is, let's say, all Americans or all people of the world. We don't really know how many people there are in the world or in America exactly. So in most cases, for the population, you're just going to write it's all who, right? You're going to tell me who is the population. It's all of these people or all of this group. And then you're going to tell me what is 10 times your sample size. So a lot of the times, to verify this condition, we're going to assume that it's true for the most part. occasionally you will know or be told what the true population size is. So then you could say, well, I know the population is this number, and it is, in fact, greater than or equal to 10 times my sample size. And then there will be no assuming involved there. So the one question we're going to look at says, according to census data, about 11% of Americans are teens. The proportion p hat of teens in a simple random sample of 1,500 Americans should therefore be close to 11%. If a national sample contains only 9.2% of teens, should we suspect that the sampling procedure is somehow underrepresenting teens and or the teen population has declined since the last census? Okay? Because we're told that there's this potential truth about teenage Americans, that it should be around 11%. We took a simple random sample of 1,500 Americans, and we only found that 9.2% of them were teens. So this is kind of on the lower side of 11%, but is it so far away from 11% that we really start to doubt the 11%? That's the question we're going to try to answer here. So first off, and we're breaking this problem down into multiple pieces here. If this was an actual test problem, I wouldn't break it down. I would just leave it as this. I would just leave it as what's written in black up here. So the first thing we're going to do is really discuss the SOCs of our sampling distribution. And I know I've got the mean and standard deviation here and not including the shape, but we'll talk about the shape as well. So calculate the mean and standard deviation of the proportion of sample that are teens. Well, what we just talked about earlier was that the mean of all sample proportions should be equal to approximately the population proportion, which we were told is 11%. So I'm going to write this as a proportion instead of a percent. All right, so this should be the mean of our sampling distribution. The standard deviation of our sampling distribution should be equal to the square root of p, 11%, 0.11, times 1 minus p, 1 minus 0.11, divided by the sample size, which was 1,500. Now, you got to make sure that this whole fraction is underneath the square root here in your calculator. And this comes out to be, I've already got it figured out here, and I always do 4 sig figs, so 0.008079 to 4 significant digits. Now, in order for me to calculate the standard deviation, there was a condition involved, and that was the 10% or the independent condition. And that was, is the population at least 10 times the sample size? Well, who is my population of interest here? Well, it really depends on, well, let's see. It depends on my units of my sample. Even though we're talking specifically about teens, our random sample was of Americans, and we just wanted to know of our sample what percent of them were teens. So really, when I say the population, we're going to have to say it's all Americans. And is it greater than or equal to 10 times my sample size, which would be 15,000? Are there more than 15,000 Americans? And the quick answer is yes, absolutely. In many, not very big size cities like our own, we have more than 15,000 people. So this will be true. So I'm just going to put a little note here that this is absolutely true. Now, in most cases, you might be dealing with a population that you have no idea what the size is. So then we'll say we're going to assume that's true. But we absolutely know there's more than 15,000 Americans. Now, the one piece that I left out here was the shape. We got the center right here. We got the spread right here. Let's talk about the shape. Well, we have no idea what the shape of the distribution of this should look like. So that's why we had the specific condition, the n times p and n times 1 minus p. Are they both greater than or equal to 10? Well, n being my sample size is 1,500, so I'm going to take 1,500 times 11%, and we're going to take 1,500 times, what, 89% would be 1 minus 0.11. And are both of those greater than or equal to 10? Well, the 1,500 times 11% is 165, which means the other really needs to be the leftover of the 1,500 compared to the 165. So if I were to take 1500 minus 165, that would leave me with what, 1335? These two numbers will always add up to be the sample size in the end. So really, you don't have to do two things of simple math here. You could just do one thing of simple math and then in your head try to figure out, all right, sample size minus this will give me this other number in here. And both of these have been verified, right? And so what this means is that we are dealing with an approximately normal distribution. And really, I could be a little bit more specific here. An approximately normal sampling distribution. So I know the stocks of this sampling distribution now. I know that it's approximately normal. I know the center is around 11%. And I know the spread, the standard deviation, is what? A little less than 1%. Okay? So now part two says calculate the probability that a sample contains no more than 9.2% of teens when the population actually consists of 11% of teens. Now, this was based on some old census data. What we're going to try to determine here is 9.2 far enough away from 11% that 11% may not be the truth anymore? Or maybe this random sample of 1,500 Americans really wasn't a random enough sample here. So we're going to calculate the probability um, that we have no more than 9.2%, which means we're looking at a sample proportion, a p hat. What is a probability? So capital P, what is a probability that we find other sample proportions that are less than or equal to? It's really not going to matter if we include the or equal to or not. It doesn't add anything to our overall probability. A 0.092. And we get to use normal CDF. Why do we get to use normal CDF? Because we verified the shape of the sampling distribution was approximately normal. And so now we get to go from really 0% or negative infinity. I'm just going to use 0 here. And we get to go up to our 9.2% with a mean of 11%, right? Our mean of 11%, and a standard deviation of 0.008079. And that comes out to be approximately what I have my calculator tell me earlier, 0.01294, if I were to do 4 sig figs again. All right. So if I were thinking of the sampling distribution, here's the mean, here's mu sub p hat is 11%, 9.2%, here's a specific sample proportion of 0.092, and here's the probability I'm calculating right down here. This is what this 1.29% represents. Okay. So now to interpret our results, okay, what does it mean that a sample of 9.2% happened when we should have expected 11%? So 9.2%, right here, let's backtrack just a little here. A sample proportion of 9.2% of teens only occurs approximately 1.294% of the time when we expected 11% to be teens. Now, the main idea we're really going to focus on in the rest of the semester is going to be how small of a probability do you need to have to really start to doubt a particular claim, like the 11%. And that particular number will be around 5%. Okay, it's really a line in the sand. Statistics professors and very smart statistical people kind of put that number around 5%. If something happens less than 5% of the time, we're really going to start to wonder if something's up. If something happens more than 5% of the time, then we're not really going to doubt it as much. All right. So with this 1.294%, we're really going to doubt, right? We're really going to, in this question here, we should suspect that the sampling procedure is somehow underrepresenting teens and or the teen population has declined since the last census. That would be the main thing we would conclude with our 1.294%. All right. So anytime we do these problems, number one, you are going to figure out what are the socks of our sampling distribution, what is the shape, the center, the spread, and then we're going to go answer the really probability question that's being asked of us. And hopefully we get to use some normal CDF in our calculators. And then we can go interpret what our results really mean. And we can discuss whether the results are okay and they're plausible, or we're going to discuss that they are so far away from the potential truth that we're questioning whether we have been lied to or if things have changed since previous things have been known. And that is all for video 3.